Okay, in this lesson, we'll talk about sequences and strings. To motivate the definition of a sequence, let's look at this example. Suppose a taxi company charges $2 for the first mile driven and 75 cents for each additional mile. A table I'll show you in a minute will show the cost of traveling anywhere from 1 to 10 miles. In general, the cost Cn, where n is the number of miles, is $2, the cost of traveling the first mile, plus 75 cents times the number n minus 1 of additional miles. That is, Cn is 2 plus 0.75 n minus 1. So here's a table of values. So notice n here is the number of miles. Applying the formula, Cn equals 2 plus 0.75 n minus 1. So when n is 1, n minus 1 is 1 minus 1, which is 0. So the first mile is $2. When n is 2, you have 2 plus 75 cents, or 0.75, times 2 minus 1, which is 1. So you get 2 plus 0.75, or 275. And you can see as n moves up, you're just subtracting 1 from n and multiplying by 75 cents and adding it to $2. And that gives you the price for the taxi cab up to 10 miles. This list of numbers that you could list as C1 is 2, C2 is 275, C3 is 350, and so forth, is an example of a sequence. So a lot of people just define a sequence as a list of numbers. Okay. But the more precise definition is this. A sequence is a function, okay, whose domain D is a subset of integers. The notation Sn is typically used instead of the more general S parenthesis n. The term n is called the index of the sequence. So if D is a finite set, we call S a finite sequence, and if S is an infinite set, we call it an infinite sequence. Consider the sequence S equals 2, 4, 6, up to 2n. The first elements of the sequence is 2. Then the second element is 4, and so on. So you could say S1 is 2, S2 is 4, S3 is 6, and so forth. The nth element, of course, is 2n, twice whatever the n is. So the way we represent a sequence like this is with this notation. The left bracket, 2n, right bracket. And n is your index. So n runs from 1 to infinity. So usually if n runs from 1 to infinity or 0 to infinity, they just write the curly brackets. And then the assumption is it goes to infinity. So when n is 1, 2 times 1 is 2. Then when n is 2, 2 times 2 is 4. When n is 3, 2 times 3 is 6, and so forth. The dot, 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 often referred to as ellipses, means it's going to infinity. Consider this sequence, a sequence T. A, B, B. So a sequence doesn't necessarily have to be a list of numbers. It can be a list of letters or combination of letters, numbers, whatever, because it's just a list. The first element of the sequence is A. Okay, the second element of the sequence is A, and the third is B, the fourth is A, the fifth is B. If the domain is T, 1, 2, 3, 4, 5, then T1 is A, T2 is A, T3 is B, T4 is A, T5 is B. So the sequence T is a finite sequence. Okay. If the domain of the sequence S is infinite set of consecutive integers k, starts at k, then you have k plus 1, k plus 2, on to infinity, and the index of S is n, we can denote a sequence like that as Sn, n equals k to infinity. If you didn't have anything on there, you would assume 1 to infinity or 0 to infinity. But if you put n equals k to infinity, then that's a notation you can use. So, for example, a sequence S whose domain is z non-neg would be Sn equals n equals 0 to infinity. If the domain of the sequence is a finite set, say I, I plus 1 up to j, so you have a starting integer I and an ending integer j and everything in between, then your sequence representation would be n equals I to n equals j, Sn. So for example, the domain -1, 0, 1, 2, 3 can be noted Sn n equals -1 to 3. So here's an example. Suppose x is a sequence defined by xn equals 1 over 2 to the n. N is integers running from -1 to 4, which means basically -1, 0, 1, 2, 3, and 4. So if I plug in -1, 1 over 2 to the -1 is the same thing as 1 over a half, or 2. So you get 2. When n is 0, you get 1 over 2 to the 0. 2 to the 0 is 1. 1 over 1 is 1. When n is 1, you get 1 over 2 to the 1, so that's a half. When n is 2, you get 1 over 2 to the 2, or 2 squared, which is 4, so you get 1/4. When n is 3, you get 1 over 2 cubed, which is 8, 1 over 8. When n is 4, you get 1 over 2 to the 4, which is 1/16. Okay. So let's look at this example. Our sequence formula is Sn equals 2 to the n plus 4 times 3 to the n. Okay. Suppose I want to find S0. In other words, what is S0 means plug in n equals 0. Okay. So S0 is 2 to the 0 plus 4 times 3 to the 0. 2 to the 0 is 1. 3 to the 0 is 1. So this becomes 1 plus 4 times 1, or 5. Okay. What if n is 1? S1 equals 2 to the 1 plus 4 times 3 to the 1. Okay. So 2 to the 1 is 2, 3 to the 1 is 3, so this becomes 2 plus 4 times 3. 4 times 3 is 12. You add 2, you get 14. Suppose I want a formula for Si. Well, all that means is I plug I in for n, which means every n in the formula just changes to an I. Okay. What about a formula for Sn minus 1? So Sn minus 1 just means everywhere you see an n, you insert n minus 1. Okay. Formula for Sn minus 2, everywhere you see an n in this formula up here, you plug in an n minus 2. So you get Sn minus 2 equals 2 to the n minus 2 plus 4 times 3 to the n minus 2. Okay. Now, we want to prove that Sn, this formula, satisfies this equation, that Sn is 2n plus 4 times 3 is the same as Sn equals 5 times Sn minus 1 minus 6 times Sn minus 2. Okay. So to do that, we'll create another page here. Okay. So now we're going to say Sn is 5Sn minus 1 minus 6n minus 2. So I already found out what Sn minus 1 is, right? It's 2 to the n minus 1 plus 4 times 3 to the n minus 1. So we're going to have 5 of those. We're going to subtract from it 6 Sn minus 2. And we already showed what Sn minus 2 was. It's 2 to the n minus 2 plus 4 times 3 to the n minus 2. Now what I'm going to do is just multiply 5, distribute 5 through these parentheses. So I have 5 times 2 to the n minus 2 plus 5 times 4 times 3 to the n minus 1. And then at the same time, we're going to distribute this negative 6 through here. So we're going to have negative 6 times 2 to the n minus 2 times negative 6 times 4 times 3 to the n minus 2. The next line, what we do is we say, okay, well, I got an n minus 2 here, and I'm just going to reorder these. I'm going to move this up to here and this over to here. So I've kind of got the powers of 3 together and the powers of 2 together. Then we're going to do some factoring. What we're going to do here on this line here, we're going to factor 2n minus 1 out of these. So if I factor 2n minus 1 out, the 6 will be by itself. If I divide 2 to the n minus 1 divided by 2 to the n minus 2, I end up with 2 to the 1, which is 2. So if I factor 2 to the n minus 1 out of here, it throws an extra 2 there. Because 2 times 2 to the n minus 1 is, 2 times 2 to the n minus 2 is 2 to the n minus 1. Okay. So then, over here, On this line, we did a couple of things. First of all, 5 times 2 is 10. I subtract 6, I get 4. So that's where that 4 came from. Here, I'm going to factor out 3 to the n minus 2, right here. I'm also, and if you'll see what happens there is you're going to get an extra 3 here because, again, if I divide 3 to the n minus 1 by 3 to the n minus 2, I get 3. Okay. Now I'm also going to factor out a 4 and a 3 from both of these terms. So you factor a 4 out, comes out, and then factor a 3 out, you'll end up with 5 left over in the first term and just a 2 in the second. And then 4 times 3 is 12. So that's where that comes from. Okay. And then 5 minus 2 is 3. Okay. So here, 4 you could write as 2 squared. So 2 squared times 2 to the n minus 2 gives you 2 to the n. This 12 you can write as 4 times 3, and then you have this extra 3 from 5 minus 2, so that's 3 squared, which means you can multiply 3 squared times 3 to the n minus 2, which will give you 3 to the n. So after all that simplification, I get the same formula right here, which means this satisfies this formula. If I take Sn minus 1, Sn minus 2, multiply by 3, and subtract 6 times S minus 2, I get that back. Okay. This formula down here at the bottom, Sn equals 5 Sn minus 1 minus 6 times Sn minus 2, is often referred to as a recurrence relation, which we talk about later on. And this is a solution to this recurrence relation. We go into that in greater detail in a later video. Okay. Since sequences are actually functions, they have all the same properties as functions, from real number functions you probably studied in earlier courses. So a sequence S is defined to be increasing if for all I and j in the domain of S, if I is less than j, then Si is less than Sj. Okay. A sequence S is decreasing if for all I, j in the domain set of S, if I is less than j, Si is greater than j. So the first one is just saying as I gets bigger, the values of Si are getting bigger. The decreasing one says as I gets bigger, then the SIs are getting smaller. Okay. A sequence is called non-decreasing if for all I and j in the domain of S, if I is less than j, then Si is less than or equal to Sj. So non-decreasing allows for the fact that they could be equal. Some comparisons could be equal, whereas the strictly increasing does not allow for that. Si always has to be less than Sj, whereas with non-decreasing, Si has to be less than, can be less than Sj, but less than or equal is also allowed. So non-decreasing means that it's either staying the same or going up. So it's either strictly increasing, it's either staying the same or increasing. So that's what the term non-decreasing comes from. And then by extension, a sequence S is non-increasing if for all I and j in the domain of S, if I is less than j, then Si is greater than or equal to Sj. As opposed to as opposed to decreasing, where if I is less than j, Si has to be strictly greater than Sj. So again, it's called non-increasing because the values of S are either equal or going down, but never going up. Okay. So here's a sequence, 2, 5, 13, 104, and 300 is increasing and non-decreasing. Okay. The sequence AI 1 over I, or I is greater than or equal to 1, is decreasing and non-increasing. Okay. This sequence, 100, 90, 90, 74, 74, 30, is non-increasing, but it can't be decreasing because decreasing requires every additional number to be smaller than the previous one, Whereas this has got, the 290s are equal, the 374s are equal. So this is non-increasing, but it's not strictly decreasing. Because again, remember, non-increasing allows them to be the same. As you go on, they can either be the same or go down, but never go up. Okay. Let S be a sequence. A subsequence of S is a sequence obtained from S by choosing certain terms of S in the same order in which they appear in S. So for example, if the sequence is A, B, C, Q, BC is a subsequence because B is in A, B, C, Q, and it's in the same order. So something like AQ is not a subsequence. To be a subsequence, if AQ is a subsequence, A would have to be next to Q in the original sequence, like BC is. Okay. All right. Suppose I take the terms of a sequence. So I have a sequence AI from I equals M to N, and I can list them out. Is a sequence AM, AM plus 1, all the way up to AN. Suppose I take those terms and I sum them up. Okay. So this is called a summation, sometimes a series. So basically, if I take the terms of the sequence and I just add them together, it generates a number. And that's called a sum. And the notation for that is I equals M to N. So this is the sigma notation. I equals M to M of AI. So what that means is you start at M, you plug M in for I. So this AI is some kind of formula in I. It generates a number, which we just call AM for the moment. You write it down. Then you increment M by 1. So now next one's M plus 1. So you plug in M plus 1 for I. It generates a number. You write it down and add it to AM. Then then M plus 2 goes in there, it generates a number, you write it down and add it to the previous 2. And you do this until you hit this upper limit I. Okay. All right. The product notation is you take these same numbers from your sequence and you just multiply them. So you see I starts at M, you plug in M, you get an A, I is a value, M, you plug it in there, the formula generates a number, we call it AM, you write it down. Then you set I to M plus 1 and you plug that in. It generates a number, you write it down, and you multiply it by the previous number. Then when I is M plus 2, you stick it in there, figure out what the number is, write it down, multiply it by the previous 2. And you just do this till you get to the top number. That's called the product. So the capital pi is a product, means multiply everything out. The sigma means add them. If it's just a sequence, you just list them out. Okay. So here's an example. Suppose if I equals 1 to 5. So I set I equal to 1, write it down. And then I change I to 2, plug in the formula. Well, if I is equal to 2, you write it down, add it to the 1. Then I equals 3, you plug it in the formula, you write it down, add it to the previous 2. So if you do this all the way up to 5, you're basically summing up 1 plus 2 plus 3 plus 4 plus 5, which is 15. Now you might remember from our video on induction proofs, we proved this formula, that the summation of I equals 1 to N of I is 1 plus 2 plus 3 plus 4 up to N. Okay. That is equal to just taking whatever that top number is N, multiplying it by the next number up and divided by 2. So if I go back and look at this previous one, N is 5. So this means 1 plus 2 up to 5. So N is 5. If I plug it in for N here, it goes there. If I plug it in for N here, I get 5 plus 1. So it's 5 times 6 divided by 2. 5 times 6 is 30. Divided by 2, you get 15. Same answer as if you just added them up. Okay. The product from 1 to 5, I equals 1 to 5. The product, instead of adding them, you multiply them. And you get what amounts to 5 factorial, which is 120. Okay. Suppose I let A be the sequence defined by AN equals 2 to the N. What is the summation of N equals 1 to 3 of AN? Well, if AN is 2 to the N, 2N, then when N is 1, AN is 2, so you write 2 down. So A1 is 2. A2 is 2 times 2, which is 4. You write that down. A3, 2 times 3 is 6. You add them. So 2 plus 4 plus 6 is 12. Okay. The product from n equal 1 to 3 of AN. So A1 is 2. 2 times 1 is 2. A2 is 4. 2 times 2 is 4. A3 is 6. 2 times 3 is 6. You multiply them. You get 48. The geometric sum is just a summation of A plus AR plus AR squared. The next one would be AR cubed, AR fourth, up to AR to the n. Okay. A is a fixed value, R is a fixed value. And notice they call it geometric sum because every term is the previous term multiplied by R. So A is the first term. The next term is A times R. AR squared is AR times R. The next term would be AR cubed, which would be AR squared times R. Okay. So this can be written this one. I equals n summation I equals 0 to n of AR to the I. Okay. Right. Changing the index and limits of a sum, you could rewrite I equals 0 to n of as I R to the n minus 1, n minus I rather. Replacing the index I by j, I could be j minus 1. And since I is j minus 1, I R to the n minus I becomes j minus 1 R to the n minus j minus 1. And if you clear that parentheses, you get n minus j plus 1 is R. So if I is 0, j is 1 in the first case. Okay. If I is 1, then j minus, rather, yeah. If I is 1, then you get I n minus j. So the summation of I equals 0 to n of I R to the n minus I is equivalent to j equals 1 to n plus 1 of j minus 1 R to the n minus j plus 1. Because if I set j equal to 1 here, I get 0, right? R to the 1 minus j plus 1 or minus j, or yeah. Okay. So you end up with 0 minus j plus 1, 1 minus j. And down here, if you plug in 0 for I, you get n minus I, or actually, I guess, yeah. Yep. Okay. All right, so these are equivalent. You just indexing them. You're changing the index and changing the formula to make them equivalent. Sometimes that's a useful thing to do. Maybe you don't want to start summing at 0. I would rather start summing it from 1. But you want to get the same numbers out. You can make that change. Okay. All right. Now let's talk about strings. What are strings? Strings are just sequences. A string over x, where x is a finite set, is a finite sequence of elements over x. So if x is the letters A, B, C, a string could be the letter B. Okay. In our textbook, beta, they use these Greek letters. Beta 1 is a string B. Beta 2 is a string A. Okay. Beta 3 is string A. Beta 4 is string C. These are all possible strings. You could also obtain a string over X. The string might be written BAAC. Okay. Because all it says is a string over X, where X is a finite set, is a finite sequence of elements from X. So it could be just one letter of ABC. It could be any combination of letters. As long as that's a finite length, you can have you can use as many characters as you want. So you can make up many strings out of the set ABC. So of course in computer programming, we make up strings out of essentially the ASCII or Unicode table. All the letters of the alphabet, the numbers, the punctuation things, you know, exclamation, pound sign, comma, and all that. Can all make strings out of it. That's the set. At the set X for a computer system is that table when you make strings in like Java or Python or something like that. You're making strings over that table is your set X. And you, as long as you have a finite size characters, you can make as many different strings as you, pretty much as you want. Since a string is a sequence, order is considered. So for example, the string BAAC is different from the string ACAB, which makes sense if you're talking about the alphabet as strings. You know, that's a different string than that. Or, you know, think of strings as words, you know, the order of the letters make different words. Repetitions in a string can be specified with superscripts. This just makes it easier than writing down the whole string. So for example, the string BBAAC could be written as B to the 2 power, which just means you're writing the B twice, A to the 3 power, which means you're writing the A 3 times, and C. So you have to make sure when you see this, you know you're talking about the context of strings, and this is not some formula involving the variables A, B, and C. That's not what this is. It's just a shorthand way of writing long strings. Okay. A string with no elements is called a null string and is denoted by lambda. We let x to the star denote the set of all strings over x, including the null string. Okay. We let x plus denote the set of all non-null strings over x. So in other words, x star is every set of all strings plus the null string, and x plus is set of all strings minus the null string. You don't want them to. Okay. The length of a string alpha, so the name of the string is alpha, is the number of elements in alpha. The length of alpha is denoted by absolute value alpha, by that notation. Okay. So if alpha is AA, BAB, and beta is A cubed, B to the 4th, A to the 32, then the length of alpha is 5, because you can clearly see there's 5 characters in it. Here, you've got 3 A's, 4 B's, 32 A's. So you can just add the numbers up. If it's written in this, superscript form, you're going to have 3 A's plus 4 B's, so that's 7 elements right there, plus another 32 A's, that's 39 elements. So the length of B is 39. Okay. If alpha and beta are 2 strings, the string consisting of alpha followed by beta is written alpha beta. That's called a concatenation of alpha and beta. Okay. So that's what a mathematician would call the catenation of 2 strings. Computer scientists would call that concatenation too. When you have one string and you just create a new string with the first string followed by the second string, you concatenated them. Okay. So for example, if gamma is the string AAB and theta is the string CABD, then gamma theta is AAB CABD. And if I reverse the order, theta gamma, you put theta first, CABD, followed by AAB. Gamma lambda is just gamma, because if I take the null string and I concatenate it with a string, all I get is a string, just AAB. Okay. Reverse the order, gamma lambda is really gamma, AAB, same thing. Okay. A string beta is a substring of a string alpha if there are strings gamma and delta such that alpha is gamma beta delta. Okay. So suppose the string beta is a string ADD. This is a substring of alpha, which is AADDAD. Since if we take gamma to be AA, the first 2 letters, and delta to be the last 2, AD, then alpha is then we have alpha is written as gamma beta delta. So in other words, the substring is the third A and 2 D's. So we made alpha the first 2 A's and delta the last 2, the last AD. So alpha is now written as gamma AA concatenated with beta, our substring, AADD concatenated with delta. So that meets our definition. So beta is ADD is a substring of AAA, DDAD. Note that if beta is a substring of alpha, then gamma is part of alpha that precedes beta in alpha, and delta is a part of alpha that follows beta. So suppose I asked, is DAD a substring? And the answer is yes. Your alpha would be AAAD, then your string is DAD, and there's nothing after it. So that makes your delta equal to lambda, the null string. And that would meet the definition, and DAD would be a substring.